Good morning, students. So the next topic in sets is intersection of sets. That comes under operations of sets. Yesterday we have learnt about the union of sets. And today the topic is intersection of sets. Consider the sets P and Q. Where P is given as 1, 2, 3, 4, 5. These are the elements of the set P. And Q is given as 5, 6, 7, 8, 9. So in sets P and Q, the common element is 5. If you see here, the common element is 5, which is given here. Therefore, the intersection of set P and Q is 5. So intersection of two sets means that element which is present in both. That is common in both the cases, both the sets. So that becomes the intersection of the given set. Symbolically, it is represented as the inverse U. Okay, that is P intersection Q. It is read as P intersection Q, which is number 5 from the given set P and Q. The intersection of two sets A and B is the set of all those elements that belong to both A and B. Alright, and symbolically we represent this by A intersection B, where X belongs to A as well as X belongs to B. The Venn diagram representation of intersection of two sets A and B is shown here. Look at this diagram carefully. We have set A and set B. Both these sets, okay, they are not covered properly, covered entirely with a particular color, whereas certain region is shaded with green color. I mean to say this region is shaded with green color. So this region is A intersection B. So this region is A intersection B. Properties of intersection of the sets. Consider two sets C and D, where C is given as 2, 4, 6 and 8 and D is given as 3, 5, 7, 9. Do you find something common, a common element in both the sets? No. So here this is called as null set. So what is the common feature here of these two sets? What is C intersection D? It will be 5, null set, because nothing is common, so it becomes null set, represented as this. Both are separate sets, nothing is common, separately drawn. Properties of sets now. A intersection B is equals to B intersection A, which we have seen earlier also in the previous class regarding the union of sets. That is commutative law. A intersection B intersection C for 3 sets. Then we can write this as A intersection bracket B intersection C, which becomes associative law. Here is nothing but the change of bracket positions. That's it. Phi intersection A becomes phi only, and universal intersection A is equals to A only. That is law of phi and universal for the intersection of sets. A intersection A will give you A, which is idempotent law, which we have seen in the law of union of sets also. A intersection B union C. This is called as distributive law. Okay, distribution of what we are distributing? We are distributing the intersection over the union. So A intersection B union C becomes A intersection B union A intersection C. So let's prove this particular thing, distributive law here. So first of all, we'll take the LHS part. LHS looks like this. The Venn diagram for LHS. A intersection B union C. It looks like this. Okay. Same value when calculated, like A intersection B union A intersection C, should look like in the same manner. Okay. So first of all, we'll see the right hand side, A intersection B, how the figure looks. A intersection B looks like this when we draw all the 3 sets. So only A and B, the common part of A and B, is shaded with green color. And when we see A intersection C, then it is only A and C regions. The common region is colored green. And when we combine both, that is the union of A intersection B and A intersection C, then what we get here? The third figure, which is this. Okay, this is the figure. Okay, so if you match this figure with the LHS part, you get the same Venn diagrams. That's all from today. If you have any questions, you can ask in the virtual class regarding operations in sets, particularly in intersections or union. Thank you.